In this short tutorial, you're going to build on your knowledge of the atom and its electrons to better understand molecular or covalent bonding. Covalent bonds are what holds this molecule together. So each of these atoms is connecting to the next atom by a covalent bond. First, let's learn to predict what kind of bonds hold together a compound. Sodium chloride is an example of an ionic compound held with ionic bonds. It's made of a sodium atom that combines with a chlorine atom. Notice that sodium is on the left side of the table, it's a metal, while chlorine is on the right side, it is a nonmetal. The periodic table is divided into two parts by a line that zigzags its way up over on this side. Everything to the left of the line is considered a metal, while everything to the right and this element called hydrogen are all considered nonmetals. So another compound, potassium nitrate, would also be considered ionic, and that's because it's made of potassium, a metal, and nitrogen and oxygen, both nonmetals. Anytime there's a metal with nonmetals, you have an ionic compound. Let's look at a few more examples. What about carbon dioxide? Now, carbon dioxide is made of carbon atoms that combine with oxygen atoms. Since both of these are nonmetals, this is a molecular compound held with covalent bonds. Hydrogen sulfide is another example of a molecular compound because it is made of a nonmetal, sulfur, that combines with another nonmetal, hydrogen. What about glucose? Glucose has 6 carbons, 12 hydrogens, and 6 oxygens all combined. What kind of compound is glucose? Correct. Glucose is also a molecular compound because it is made of all nonmetals. Now let's use your knowledge of electrons to understand why these compounds bond the way they do. Recall that carbon has 6 electrons, represented by arrows in an orbital diagram. 4 of those electrons are called valence electrons. Now in these drawings, we've done something interesting with the outer S and P shells. These two shells have been combined into one. They've been hybridized. In fact, this hybrid has a special name because it's made of 1 S and 3 P orbitals. It's called an sp3 hybrid. We don't need to understand hybridization yet, but I did want to explain why the electrons are spread out the way they are. You might have expected to see the electrons like this, with 2 electrons in the 2s orbital and then 2 more in the 2p orbital. But again, with hybridization, all of these orbitals kind of mix together and act as if they're the same. Another way to show this is using our Lewis dot diagrams. So carbon's diagram would look like this, with 4 dots for the 4 outermost electrons. In either diagram, you probably notice a problem. Atoms are looking for a full set of valence electrons, what we call an octet, or 8. Carbon only has 4 so far, and that's where the hydrogens come in. Hydrogen has 1 electron in its 1s orbital, and it also would like to have a full orbital. By sharing with this carbon, hydrogen can get a full orbital, and this forms what we call a single covalent bond. We can also represent this in a Lewis dot diagram like this. So hydrogen has its electrons, but carbon still needs some more. Even counting this shared valence electron, carbon still only has a total of 5 valence electrons, and so it needs to share some more. With 3 more hydrogen atoms all sharing their valence electron, carbon ends up with 8 total valence electrons. Represented on our Lewis structure, it would look like this. Now let's count the valence electrons around carbon. 1, 2, 3, 4, 5, 6, 7, 8. Recall that shared electrons count for both elements. So hydrogen would count 1, 2 electrons, as would this hydrogen here and here and here. All the atoms have a complete shell. They are stable and happy. Let's look at another example. Fluorine is an atom that has 7 valence electrons. It's just 1 electron short. You might remember seeing fluorine before, and it was excellent at stealing electrons to fill that last spot. However, what if there were no elements to steal electrons from? What if there were just fluorine atoms? The two fluorine atoms, each being short one electron, have an interesting solution. Instead of stealing electrons, they share this outermost electron, overlapping their orbitals, and both electrons are now satisfied. This also could be represented with a Lewis dot diagram. So my first fluorine atom has 7 valence electrons, and so does the second one. By sharing this pair of electrons here, they essentially each gain a full octet, and now we've got a stable molecule, represented with the formula F2 for the two fluorines that combine. Ammonia is another example of a molecule that uses covalent bonding. The nitrogen atom has 5 valence electrons, represented in this drawing. Hydrogen has 1 valence electron. Sharing this pair of electrons helps nitrogen along its way to gaining a full octet. If nitrogen could find 2 more hydrogen atoms to share with, it would gain an octet of electrons, and now represented with a Lewis structure. Our next example is a very familiar compound of water. Let's look at the electron structure for water. Oxygen has 6 valence electrons. Each hydrogen has 1 valence electron. By sharing a pair of electrons with each of the hydrogen atoms, oxygen gains an octet, becomes more stable, and the hydrogens also become more stable. Here's the Lewis structure for water. In our last example, we're going to look at a slightly different situation. Oxygen is an atom that has 6 valence electrons. It's 2 electrons short from having an octet. In our last example, we saw oxygen sharing electrons with 2 different hydrogens. But if there were no other elements, if it were just oxygen, oxygen might also share electrons with other oxygen atoms. When these electrons are shared, oxygen is a little bit closer to having an octet, but it's still short 1 electron. So this oxygen has 1, 2, 3, 4, 5, 6, 7. What's the solution to this problem? Simple. We'll share 2 pairs of electrons. On the Lewis structure, that would look like this. We're going to move these electrons over here so that they also can be shared. Now, let's count the valence electrons in this compound. 1, 2, 3, 4, 5, 6, 7, 8. That's a happy oxygen atom. My other atom also counts all of these electrons. 1, 2, 3, 4, along with these, 5, 6, 7, 8. And we have another happy oxygen atom. That's a stable molecule. I hope this short lesson helps you understand what's going on with covalent bonds and how these are different from ionic bonding. Good luck as you draw your own Lewis structures to represent molecular compounds.